All right. Real number system is the way we count numbers. You all know how to count. If this was, grade 1 and Mrs. Bad Crumble was at the front of the room and she said, okay, everybody, let's count how many of us are in the classroom. Let's count together. And she would do this. And you would all go, because you lived to keep your grade 1 teacher happy. It was your favorite thing in the world because you loved school. It was the greatest thing ever. I don't understand what happens between grade 1 and grade 10, but, But I don't want to teach grade 1. I don't want to go back to that because my wife teaches kindergarten and sometimes she has to clean up poo. And I have never had to clean up poo, which makes me perfectly happy. But my wife does not want to deal with students who will call her an effing bee, like sometimes students have called me. So it works out both ways. Anyway, back to business. If Mrs. Bad Crumble said, you would all go, and how would you all count? Everybody count with me. How many students are in the class? Everybody go. Stop. We all started with 1, correct? Automatically, we started with 1. Is 1 really the first number? No, of course it isn't. But we all started counting with 1, yes? That is what the natural numbers are. The natural numbers are 1, 2, 3. How far can we count? To infinity. Will we ever get there? No. So it's 1, 2, 3 up to infinity. And these are what I like to call the counting numbers. Everybody cool? Now, believe it or not, and this doesn't make a lot of mathematical sense, but it's a good way for you to think about it. This is the smallest section of our number system. Even though it goes all the way up to infinity, it's technically the smallest section. Everybody cool? All right. The whole numbers. The whole numbers. Now, all of you, when I say whole numbers, you automatically start thinking fractions. Even if you've done this lesson with your teacher in the past. You are automatically thinking, whole numbers are fractions. That's what they is. If I wrote 4 3/4, you would all say the whole number was 4, right? Okay, that's not what it really is. The whole numbers are the natural numbers. So 1, 2, 3, 4, 5, 6, 7, 8 up to infinity plus 0. So these guys are 0, 1, 2, 3, up to infinity. Now, hopefully you are already see that even though there's an infinite amount of numbers here, there is an infinite amount of numbers here and one more, right? So it's ever so slightly bigger, even though they're both infinite. Do you understand what I mean? Everybody's understands? Okay. The next group is the integers. Now, the integers are the naturals. Oh, I don't want to use black again, dummy head. Are the naturals plus the negatives. So that is -3, -2, -1, 0, 1, 2, 3. Up to what? Positive infinity. And down to what? Negative infinity. So you should be able to see it's almost like a pyramid, yes? The smallest group, the natural numbers, fit into the next group, which fit into the next group. Is everybody cool? Now, right there, I need you to draw a line. Because those three groups are missing a lot of numbers. In these three groups, there are no fractions, which automatically means there's no decimals. So, natural, whole, and integers, no fractions, no decimals. The reason it's important is when we count data, okay? For example, how many students are in this room? Well, there's a couple of people missing. So, but let's say 30, right? If another kid walks in there, how many kids are in the room? 31. Is it possible to have a fraction of a kid in the room? No. So that's why it matters if we have whole numbers, integers, or natural numbers. As a matter of fact, is it possible to have a negative amount of kid in the room? No. What's the lowest amount of kids that can be in the room? 0. So how we count which part of the real number system we are using is important when we are actually representing data. Does everybody understand? Right? You can't have, like, I have 2 kids. I can't have 2.5 kids. Right? Okay? Like, it just doesn't work. Well, I have a half brother. Yeah, that doesn't mean that he's only an arm and a leg that hops into the room and says hello. He's still a whole person. Right? Everybody understands? Okay. But you're intelligent young people. You're aware that fractions and decimals exist. They must, because you can fill your gas tank half full. You can have $50. You can drink half a can of Coke. So all this stuff exists. Those are the rational numbers. The rational numbers are all the fractions. Now, a real fraction has to be in this form. X and Y are integers, which means they fit into this container, and Y cannot equal 0. Because if Y is 0, it's impossible. It's infinite. You can't, it doesn't exist. Okay? Now, all the fractions. And you say, okay, Mr. Myers, what about decimals? Decimals too. Except the decimals must repeat. So 333.373737, something like that. Or the decimals must terminate. And terminate means end. 0.3762. That ends. So it's a rational number. Everybody cool? Easy up to there. The whole lesson here is easy. There's nothing complicated about it. We're all good? But again, we still haven't covered all the numbers. We make a line there because all of these guys, and I know that's gender specific, I apologize, all of these numbers work together. They're buddies. They will hang out all the time. But there are a bunch of numbers that don't fit in. They are the irrational numbers. And they are weird, meaning they are nothing of the above. If they're a decimal, they never end. They never repeat. You cannot make a fraction out of them. What's the most famous one? Pi. Everyone's, well, isn't pi the circumference divided by the diameter? Yeah, it is. Isn't that a fraction? Yeah, it is. But when you do with the calculator, circumference divided by diameter, you end up with a decimal that never ends. At least not in the first billion or so places. That there's a computer in MIT in Massachusetts, or one of those nerdy schools out there, that has been working on pi for like 60 years. It's up in the billions or trillions of decimal places, and it hasn't repeated yet. It's not going to. So pi is the most famous one. But there's a bunch of others. A little later in your life, you're going to learn about E. It's on your calculator. You can see E with a little x. That's another famous irrational number. It's like 2.78, blah, 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 forever and ever and ever and ever and ever. It's used in finance math. But more importantly for you people, irrational numbers are non-perfect squares. non-perfect square roots. For example, the square root of 1 equals 1, the square root of 4 equals 2. Correct? Everyone knows that, right? 2 is a rational number, isn't it? It's 2 over 1, and it's an integer, and it's a whole number, and it's a natural number. Everyone's good with that, right? Okay, but what exists in between 1 and 4? There would be the square root of 2 and the square root of 3, right? If you do them with your calculator, your whole calculator screen fills up, doesn't it? Why does it stop there? Because your calculator runs out of room. How far will these two decimals go? Forever. And they will never repeat, and they will never terminate. So anytime you have a square root that fills up your whole screen, that's an irrational number. Is everybody good? Everyone's cool? Okay. Let's turn the page over. Let's do some converting to fractions, just to make sure everybody can still do this. What's that as a fraction? 12 over 100. Now, would you be allowed to hand that in as the right answer? In my class, because that's what it is. But you've had teachers that would take marks away if you handed it in that way, wouldn't they? And I won't take marks away, but will I give you the full 4? No, because what is that really? That's really 3 over 25, right? Everyone's cool with that, yeah? Okay. What's this one? Some of you know the trick already. What is that as a fraction? 1 over 9. How many of you were taught a repeating thing is 1 over 9? How many of you were taught why a repeating thing is 1 over 9? So you're just taught a repeating thing is 1 over 9. So that means you all automatically know what the answer to D is, because there's a repeating thing in there, right? So what is it? 54 over 99? Try that with your calculator. Tell me what you get. So, yeah, it's great that you all learned the shortcut that something repeating is over 9. But it's not really that useful if you don't know why it works, right? Here's why it works. Isn't 0.1111111 forever very close to 1/10? Which would be 0.1, right? That's 1/10. Do we agree? All right. Now, a fraction has to have an integer there and an integer there, doesn't it? Okay. So is 0.111111111 ever so slightly bigger or smaller than 0.1? It is ever so slightly bigger, yes? So to be a fraction, it must be 1 over something. What is the next integer that is bigger than 10 as a denominator? 9, because 1/9 is ever so slightly bigger than 1/10. That is why this works. Everybody cool? So, if I want to go out 2 of them, 1, it's 11 over 99, 1/9. If I want to go out 3 of them, it's 1 over 999. Cool? Excellent. What about this one? This one's a little tricky because people don't really know what to do with it. What do those 3 dots mean? It keeps going. So what is our best assumption for C? Because we don't know. Our best guess is 2/9, right? Because the 2 repeats. Why have I stressed estimate, best guess, and we don't know? Doesn't have a little bar over it, does it? All I know is this goes on and on and on. It might be 2 till infinity. but there might be a 7 in there somewhere. So this is a guess. Is everybody cool? All right. Now let's talk about this one. Because as soon as you see the repeating, everybody wants to do 54 over 99, right? That's what everybody wants to try. Yeah. So if I go 54 divided by 99, I get 0.54545454, but only the 4 repeats. So it can't be that, can it? All right. So does anybody know a trick to do this? Pardon? Make the 5 a whole number? Okay. Do you know a trick, Parm? Same thing? So what do you mean by that? 5 and 4 over 9? But that's 5.444444, and I need 0.54. So you're on the right track. So 50, what? Nobody knows? Nobody's seen a trick for this? Because what they're saying, if I do 5.4444, that's 5 and 4 over 9, yeah? Okay, but that's not what I need. We've established that. There is a trick for this. I'll show you the trick I learned. You take the 54, right? But you subtract what doesn't repeat. So what part of that doesn't repeat? The 5. And that gets you 49. Now, what repeats? The 4. Right? Anything repeats has to be over 9, yeah? Does anything else repeat? No, because the 5 doesn't repeat. So what number shows nothing? 0. And if you do 49 divided by 90, that's the trick I was taught. It's not really important. I just wanted to show it because everybody knows this trick, and then they think they know this trick. But it doesn't work that way. That's the trouble with teaching tricks. They don't always work. All right. So let's look down here. Put it in the appropriate category. Does the number 14 have a cube root? Of course not, because 3 cubed is 27, 2 cubed is 8. There's nothing between 8 and 27. So if this doesn't have a cube root, is it rational, irrational, natural? What is it? Irrational. Easy peasy, lemon squeezy. And if it's irrational, that's the only category it fits in, yes? Okay. What about the square root of 25? What is the square root of 25? 5. What categories does 5 fit into? Is it natural? Yep. Is it whole? Yep. Is it integer? Yep. Is it rational? Yep. So if it fits in the top of the pyramid, it fits all the way in. Like those little Russian dolls. You know what I mean? Okay. I'd like to know what they were called, but I can never remember what they're called. And there's not a lot of Russians in Abbotsford to tell me what they're actually called. Any of you Russian? Ukrainian? Slavic of any kind? Jack, what are those little dolls called? Ask your grandma. Or is she not the Russian one? Who's Russian in your past?
No, I'm Ukrainian.
You're Ukrainian. Who's Ukrainian in your past? How far back? Your grandma? Do you see her a lot? Will you see her before tomorrow? Damn it, that means I'd have to use the actual internet. How will I get time to actually internet something between all my tweeting and Instagramming? Man. Oh well. Anyway, it's like those Russian dolls. So if it's natural, it's automatically everything else, right? All right, now this one's tricky. What is it? What's C? Madeline says irrational. Who agrees? So that means 26 of you don't agree? Okay, so why do you disagree, Sihaj? Why do you say C is rational? Because that's the only other option. If something's not irrational, it must be rational. So why is C, do you think, rational? Because I know that, Madeline's changed her mind. You convinced her, Sihaj. You didn't even have to say anything. That's charisma. Well done. Why is it rational? Because it ends, right? This is 5 and 319, 754 1/millionths. It ends. What if I put those dots there? What would you say? Irrational would be your guess or truth? Guess, because maybe the next numbers are 319,754. But you guess irrational. Everybody good? Okay, let's keep rocking. Oh, exponents. What's D? Rational or irrational? It is rational. Is it anything other than rational? Is it an integer? Is it a whole number? Madeline says yes because it's positive. Is it positive? I see a negative base. Is it positive? Of course it is, because what is it really? It's really 16. So is it natural? So does that fill in everything else? Okay, what about E? E's easy. What is it? Natural. What's F? What happens with your calculator if you do the square root of -4? Doesn't work, because this number doesn't exist. This number is an invention, so we could explain other things in math. This is what we call an imaginary number, because it's not the real number system. You guys thought math was hard when you only had to deal with the real numbers? Wait until you have to start dealing with the imaginary numbers. Don't worry, it's not until second year calculus. So you have to be in second year of university, and you have had to pass Calculus 100, which is the hardest course in the history of all academics. Calculus 100 is, it will walk in, it will spit in your face, kick you in the junk, cut out your kidneys, and sell them on the black market. That's how tough Calculus 100 is. 6 out of every 10 kids fail it. Not do badly, fail. 6 out of every 10. I know, right? So, Calculus 100 is hard. Okay? What about G? What's your best guess? Rational. Why? Because it looks like it repeats. But what if the 327th decimal was a 7? Do we know? No. So we would guess that to be rational based on looks. Everybody cool? Parm. Oh yeah, you would just write, it's a big, I can't remember you would write a big I. There's a different letter they use to show if something's irrational, not I. I can't remember what it is, though, right now. Because I'm too busy writing comedy in my head. Okay. All right, this page, not very important, except number 6. Have a look at number 6. Talk about 6A and B with the person beside you. This right here says root 150. Talk about A and B with the person beside you and explain them. The answers aren't there, so you got to explain. The explanations aren't there. Is this number rational or irrational? Rational. Why? Because it ends. Okay? Is this number rational or irrational? Irrational, because that decimal will go on forever and ever and ever. So please notice, the square root of 150 is irrational. But the number your calculator gives you is a guess. It's rational. If you were to square this, you would get 149.999999 forever. But you would not get 150. Does everybody understand? Everybody cool? Why does it matter? It doesn't really until you're dealing with really high-level math, right? Like if I take my calculator and I do 12.24744 squared, 149.99789, right? But if I do the square root of 150, and I get that, and then I take that answer and I square it, it comes back to 150 because it is 149.99999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999. But it's not 150. Do you all understand? When the square root sign is still there, it is irrational. Everybody cool? All right. Turn the page over to page 22. We are going to talk right now about something you did in about the 5th grade, probably. And you did it in the 5th grade, and then you never did it again. And nobody told you why you had to do it in the 5th grade, but you were just like, yes, Mrs. Bad Crumble, I will do what you are asking me to do because I love you. I sometimes forget and call you Mom. How many of you have done it? Put your hands up. You've all called one of your female teachers Mom growing up. I've done it. Oddly, very rarely do I get called Dad. It happens maybe once every 3 or 4 years. Somebody says, hey, Dad, when I'm walking by, and I'm like, okay. Which was okay now because I'm 44, and you've seen my kids. They're in grade 9, almost grade 10, and grade 7. So I'm old enough to be your dad. But when I first started teaching, I was 21. And I was teaching grade 10s. Hey, Dad. I'm 5 years older than you. It was weird. Anyway. And back then, all the parents were older than me. So it was weird to talk to the parents. Now all the parents are about my age. But as I keep going, you guys will stay the same age. Your parents will stay about the same age. But I'll be getting older and older and older. And sooner or later, I'll be like 59. I'll be talking to 35, 40-year-old parents, which is going to be weird for me. Sometime I may be talking to one of your children, which is even creepier, because that might happen. It probably won't, because I'm getting the hell out of here before I'm that old. But it's possible. Anyway, sorry. Where was I? Oh, Mrs. Bad Crumble. Yes. I will do what you asked me to do, Mrs. Bad Crumble, because I love you. And you didn't know why. and you did all the work, and Miss Bad Crumble gave you your gold star on your sheet of paper, and you were like, yeah. Right? But here we are in the 10th grade, and all of a sudden, all that stuff Mrs. Bad Crumble taught you that you thought you were done with in grade 5, it's coming back. And this is the next part of it that comes back. All of you did this in grade 5 with Mrs. Bad Crumble. She gave you a number, for example, 12. And she asked you to break that down into factors. So you drew this little fun tree thing, right? All of you have seen that. Now, some of your Mrs. Bad Crumbles grew their trees sideways, right? Some of your Mrs. Bad Crumbles drew their tree up in stairs, like this. Everybody has seen this, though, yes? Okay. And that was the end of it, wasn't it? Once you made the little tree, you were done, right? And you got your gold star, and then you went out for recess and fought with the kids to get on the swings. But the duty mom wouldn't let anybody on the swing. So you'd have to go and tattle, and then the duty mom would be like, you get 1 minute on the swings. And then the next kid would come on the swings, and he'd be talking to his friend, and he'd be talking to his friend for a little while, then he'd hop on the swing, and the duty mom would go, that's your 1 minute. And you'd be like, but I only swang for one swing. That you was your 1 minute. Tough luck. How many of you have had that problem? None of you? Oh, weird. It happens all the time. Anyway, now we're going to do something with it. But first I need to remind you, what Mrs. Bad Crumble was doing here was she was providing the prime factorization of numbers. Prime numbers are very powerful numbers. They are the numbers that exist. They only have two factors, one in themselves. 2, 3, 5, 7. What's the next one? 11, 13, 17, 19, and so on and so on and so on. There is no pattern to them. Recently, a computer discovered the largest prime number, and it's like up in the billions, which is really crazy to me that a number that big can have no way to divide it except by 1. That boggles my mind, but it does exist. Everybody cool? Prime numbers are very important because they allow us to break down big numbers into numbers we can work with. All right? Now, the most powerful prime number is 2. Why? Pardon me? No. Sihaj. Yeah, it's the only even prime number. So it's very, very powerful. Okay? So what we do, first, we go back to grade 5. So let's go back to grade 5 and make a factor tree of 54. Everybody go ahead. Some of you, almost all of you, I know what your first branch is going to be. I'm not going to draw them in. You're all going to draw in a different number than I'm going to put there because I want to show you that it doesn't matter what you start with. Everybody put your first 2 branches. I would bet all my gummy bears that every single one of you are going to have the same 2 numbers there. And I am betting that almost all of you, if not all of you, have 9 and 6. Right? Right? Some of you might have 18 and 3. Ooh, badass. Some of you might have 27 and 2. Ooh, badder ass. Doesn't matter what you start with. I'm going to start with 18 and 3. Now, I'm stopping at 3. Why? Because 3 is a prime number, so I'm going to put a circle around it. 18 is going to break down to 2 and 9. Why am I stopping at 2? Prime number. 9 is going to break down into 3 and 3. Circle, circle. Now, I have to do the next step from this point. All of you got to here. If you went 9 and 6, you got 3, 3, 3, 2. And you ended up with the same thing, right? Doesn't matter. The next step that Mrs. Bad Crumble probably didn't teach you is we write this out with exponents because she didn't want to teach you exponents because she didn't have to. This is 2 times 3 cubed, right? Because 3, 3, 3, there's 3 3s, 3 cubed, and a 2. Everybody cool? Easy peasy lemon squeezy, right? All right. Do the same thing with 162. Man, 162 is a bigger number. That's bigger than 12 times 12, Mr. Myers. I don't know the times table's bigger than 12 times 12. Most of you probably don't know your times table's up to 12 times 12. But I'm not trying to put you down or nothing. You didn't have to learn them. We weren't allowed out of grade 3 unless we had them memorized. So, since it's bigger than 12 times 12, what would be a real smart number to start with? 2, because it's even. 2 and 81. Now, 81's super easy because that's in the 12 times 12 box, isn't it? What's 81? 9 times 9. Can't stop there. 3 times 3. And 3 times 3. And then we write it out. 2 times 3 to the what? How many 3's do I have now? 4. Everybody cool to there? Right? Okay. So we've got our Mrs. Bad Crumble, and now we've got something new that we're going to do with it. Everybody good? All right. Greatest common factor is, I don't want to write that in red, idiot, is the largest factor shared by a group of numbers. When do we use greatest common factor? This is how we, and I'm going to change colors to a different shade of green because all my green stuff is going to be greatest common factor. This is how we reduce, and I'm putting that in quotes because you're not reducing. This is how we reduce fractions. If I have 14 over 21, what is that really? 2/3. Because we divided both of those by 7, because 7 is the biggest number that goes into both of them. You all use GCF all the time. You just don't think to call it greatest common factor. Because you all are all the time simplifying fractions, right? Okay, so that's when we use it. Here's how we can find it when the numbers are big. Because 1421 is super easy to work with, right? We can all see that like that in our heads, yeah? But numbers get bigger than 14 and 21, don't they? Okay, so a GCF can be found using prime factorization by writing out all the factors with exponents and choosing all common bases and the biggest exponent. So, we had 2 times 3 cubed, right? Up here in 54, yeah? And we had 2 times 3 to the 4th, yeah? Have I written them all out with exponents? All done? Okay. I've written them out with exponents, right? So if I'm going to be working with the GCF, which I'm going to do in green, I had 2 times 3 cubed, 2 times 3 to the 4th. What is common to both of them? What base is common to both of them? There's a 2 and a 3, correct? The biggest exponent. What is the biggest exponent that 2 has? 1 times, what is the biggest exponent that 3 has? Sorry, not biggest exponent, idiot head. That's the next one. Smallest exponent. What's the smallest exponent that 3 has? 3. So that is 2 times 3 cubed, which is 2 times 27, which is 54. And that makes sense, because 54 divided by 54 is 1, so 54 is a factor of 54, because 1 times 54 is 54. Is everybody good? GCF is the easy one. Everyone good? All right. Let's see if you actually are cool with that. Let's do 96 288ths. I want you to simplify that. That's yucky, right? So let's break it down. 96, 12 times 8, 2 times 6, 2 times 3, 2 times 4, 2 times 2. So 96 is 2 times 2 times 2 times 2 times 2. 2 to the 5th times 3. Agreed? 288 is 144 times 2. 12 times 12. 2 times 3. 2 times 6. 2 times 3. 2 times 6. 2 times 3. And I see 1, 2, 3, 4, 5 2s, and 3 squared. So what is my GCF? 2 to the 5th times 3. Because this guy only has 1 3 to give, even though this guy has 2. So that is 96. So I can divide these both by 96. Everybody cool? That's how we use it. Oh, I went over half the page. I didn't mean to do that. That's okay. We're smart kids. We'll sort it out. What color do I want to use? I'm going purple. A lowest common multiple, LCM. That is the smallest. Oh, damn. Oh no, I left the A and the EX. That is the smallest number which shares your whole group as a factor. So when do we use lowest common multiple? Again, we use it for fractions. This is how we add fractions. 1/2 plus 1/3 means we got to be over 6. 6 is a lowest common multiple. But your teacher called it lowest common denominator. Right? That's how we use it. Again, really easy when it's 3 and 2, but a little more difficult when the numbers get big, right? And how do we find it? We find it again by using prime factors. Same thing, we write them all out. And we count everything once, but only with the biggest exponents. Count everything once. So let's come back to here. We had 2 times 3 cubed, 2 times 3 to the 4th. Count everything once. So 2 is in both of them. What's the biggest exponent 2 has? What's the biggest exponent with 2 here? 1. 3 and 4. What's the biggest exponent here? 4. So the lowest common multiple is 162. And that makes sense because 3 times 54 is 162. 1 times 162 is 162. Everybody good? Here's a little thing you need to remember at the bottom in orange. GCFs are smaller than your group. Smaller than your group or equal. And LCMs are bigger or equal. Because multiples go up, factors go down. Everybody good? All right. Let's turn the page over and we'll start with a couple of easy ones to make sure everybody can do it. GCFs I did in green, right? So first thing we got to do is factor trees. How am I going to break down 36? Madeline would like to do 6 and 6. Is that okay to start with? Everybody happy with that? Could I have done 9 and 4? Could I have done 9 and 4? Could I have done 12 and 3? Could I have done 18 and 2? All of them were acceptable, yes? So can I stop at 6 and 6? No, what's next? 2 and 3, can I stop there? Stop at those branches. And here, 2 and 3 again. I'm going to stop at those branches. Now, I'm going to do 120. What's a good breakdown? Pardon? 10 and 12? Why would you use 10 and 12, Saihash? Why did you know 10 would work? Because it ends in 0. Cool. So all those little tricks that Mrs. Bad Crumble taught you for dividing, this is why she taught them to you. So you could use them later on. Can I stop at either of them? So what's next for 10? 2 and 5. Can stop at both of them. What about 12? 2 and 6. Can stop at 2 and then 6. 2 and 3. Everybody cool? All right. So, next thing is to write them all out in exponent form. What is this one? 2 squared, not plus, times 3 squared, right? Because factors is all about multiplying. And what's this one? 2 cubed times 3 times 5. I like to keep them in order. Everybody agree? All right. GCFs we worked on in green, right? That means we compare them. 2 squared times 3 squared. 2 cubed times 3 times 5. GCF means I take whatever's common and the smallest exponent, right? Is 2 common to both of them? Yes. And what's the smallest exponent? 2 squared. Because this guy has 2 2's to give, but this guy has 3 2's to give. And I'm looking for the greatest amount that is common. Everybody good? So how many 3's are common? 1 3. How many 5's are common? None. Right? So there's no 5's common, right? So I could write 5 to the 0, but I don't need to write 5 to the 0, do I? Because that's just 1, right? So maybe for my thinking purposes, I want to have 5 to 0, because 5 is there, but there's no 5's that are common. Everybody cool? So what is 2 times 2? And what is 4 times 3? 12. And what is 12 times 5 to the 0, which is 1? 12. So that is my GCF. Everybody with me? All right. Now in purple, we did our LCMs in purple. I write it out, same thing. 2 squared times 3 squared, 2 cubed times 3 times 5. Now I got to count everything again, but now I'm looking for the biggest exponents. So, what's the biggest exponent here? 2 cubed. What's the biggest exponent here? 3 squared. What's the biggest exponent here? 5 to the 1. And then I just do the math. What's 2 cubed? 8. What's 3 squared? 8 times 9 times 5, which is 360. And that makes sense, doesn't it? Because 36 times 10 and 120 times 3. Everybody cool? GCFs? Everything with the smallest exponent. LCMs? Everything with the biggest exponent. Everybody got it? All right, let's try 18 and 24. How am I going to break down 18? 2 and 9, 3 and 3, right? How am I going to break down 24? 12 and 2, 2 and 6, 2 and 3, right? Okay, let's do this. In green, 2 times 3 squared, 2 cubed times 3, right? Everything common with the smallest exponent. So what's common here? 2 with what exponent? 1. What's common here? 3 with what exponent? 1. What's 2 times 3? 6. And we can see that. That's it right away, can't we? We know that 6 divides into 18. We know that 24 divides into 18. Right? Now, if I gave you this, don't write this down. If I gave you this back in, grade 3, Mrs. Bad Crumble might have said, well, that's 1 and 18, 2 and 9 and 3 and 6, right? And then 24 is 1 and 24, 2 and 12, 3 and 8, 4 and 6. And you would see that 6 was the biggest one in both lines, right? I don't know if that's what she would have taught you. That's what my Mrs. Bad Crumble taught me in grade 5. But her name was Mrs. Cherkasov because her husband was Russian. I could have asked her what those stupid dolls were. If only I could have seen the future. Okay. LCM. Now I want the biggest exponent. 2, 2 cubed, 3 squared, 3. What's the biggest exponent for the 2's? 2 cubed. What's the biggest exponent for the 3's? 3 squared. 2 cubed is 8. 3 squared is 9. What's 8 times 9? 72. And I'm done. Is everybody good? Super easy, right? Super easy. You guys do C by yourselves. Go. Is everybody good? GCF, count everything with the smallest exponent. LCM, count everything with the biggest exponents. Everybody good? All right, now in your book, you only have 2 numbers for D, right? But you're too smart for that. You're going to do 3. You're going to do 12, 35, and 84. And you're going to find something weird. How many factor trees will I need? 3. Can I even do a GCF? No. Because there's nothing common to all 3. Does everybody understand? So my GCF here is what? The only number that divides into everything. What is it? No, 1. Because there's nothing common to all 3. Right? So 2 is common here, correct? But it's 2 to the 0 because there's no 2 there. Yeah? Times 3, 3. Oh, but no 3 there, so it's 3 to the 0. 7, 7. Oh, no 7 there, so it's 7 to the 0. 5, so it's 5 to the 0. What's 1 times 1 times 1 times 1? 1. So the GCF is 1. Sometimes you will not find a GCF, but you will always find an LCM. And the LCM we work with in purple, highest exponent. What's the biggest exponent of 2 I see? 2 squared. What's the biggest exponent of 3 I see? 3 to the 1. What's the biggest exponent of 7 I see? 7 to the 1. What's the biggest exponent of 5 I see? 1. So 2 squared, 4 times 3 times 7 times 5. 4 times 3 is 12. 12 times 7 is 84. 84 times 5 is 420. Oh, that was an accident. Everybody giggle. Let's get it out of the way now. Yeah. Cypress Hill was awesome if you went down to the concert to protest in the country that allows you to smoke dope. So we need to have a protest about it. Stupid. Everybody good? Easy peasy, right? Okay. I am shutting up. It is 12:012. It is 12:012. I bet I paused it there when I told you to do it by yourself. I bet that's when I paused it. So the only thing you didn't see was the zeros thing. 2 to the 0, 3 to the 0, 7 to the 0, 5 to the 0, because none of them repeat. That's the only thing you really missed. So the GCF was 1, because that's 1 times 1 times 1 times 1. And then all that other funny stuff I said. And this stuff. About how if you can do that, you probably don't need to do A, B, and C. Same with 5 and 6. Gouda? Hey, I'm going to do another joke now. Everybody ready? Gouda? What's Gouda? Cheese. So Gouda, and you all say yeah, and then I say great. Grate, because that's what you do to cheese. Huh? You don't want to go home, Jaginder. If you wanted to go home, you wouldn't be back here tomorrow. And you will be. You're all going to be back here tomorrow because this is good entertainment. All right, so the first one is negative a to the 9th, negative g, 1 over g to the 6th, and it is all negative. Everybody cool with that one? That one's a bit tricky right off the top. Is everyone cool with it? Anybody need to see g? Okay. Now, some of you may have written it this way. That's okay too. All right? Some of you may actually, hold up. It's actually positive because, of course, a negative base to an even exponent is positive. Everybody cool? This is w to the 5. This is negative s to the 12th, which is, of course, s to the 12th, because a negative base and an even exponent. Everyone is good still? Stop me if you are not. X, y to the 5th, 1 over x to the 6th, and 1 over x to the 6th. Everybody okay there? xy and e squared f to the 14th over g to the 10th. Everyone okay there? That's where it starts to get a little... Yep. All right. So, split it into 3. There's e to the negative 4 over e to the negative 6. F to the 5th over f to the negative 9. And g to the negative 8 over g squared. There's a lot of different ways to think about this. You have to know what you're comfortable with. I don't do these the way most of you would, because I've been doing this longer than you have. But most of you are just going to follow the laws, right? So this is subtraction, yeah? So this is e to the negative 4 plus 6, which is e to the 2, right? This is f... That should have been blue. F to the 5 minus 9, which is 5 plus 9, right? 5 plus 9, which is f to the 14th. Yeah? And this one is g to the negative 8 minus 2, which is g to the negative 10, which can't exist. So it has to go down to the denominator. And you end up with e squared, positive exponent, f14, positive exponent, and then you ended up with g to the negative 10, which you can't have, so it goes to the denominator and becomes positive. Is everybody good? Now, lots of different ways you could think about that, right? You could have done this. You could have said to yourself, self, this negative 4 and negative 6, well, this negative 4 of them are covered down here, so they're all canceled, leaving me with the negative 2 in the denominator, which would have had to come up. 5 and negative 9, well, all those negative 9s have to come up here. 5 and 9, there's your 14. Here, all those 8s had to go down there. 2 and 8 is 10. Lots of ways you can think about it. Up to you to figure out what works for your mind. Everybody cool? All right. Keep working. Now that you've seen a few, you should be better equipped to handle these ones. The tough ones are on the back. It's 12:40. I wanted to go over the test at 12:50. fitty. And then if I ran out of time, or if I got through the test before the end of the day, you would have more practice time. So 9 more minutes, then I'll do this side, then we'll go over the test. Okay? Melina, of course you can. Now, ladies and gentlemen, you do not get to keep your tests. Okay? You get to keep your cumulatives because I make new cumulatives every year, every summer. I use the same tests every summer. Okay? Normally I trust students, but last year there was an incredibly bad ring of cheaters in my room. So now I don't let you keep the tests. Okay? So I want you to be able to use your test to study from in this room, though. So what you need to do is when I hand you your multiple choice, you may want to write your answers on here, and then you may want to just write the right answers on here when I go over it so you can study from it, okay? Then it'll be available in the room. You can look at it any time between now and the final. Then you can throw this out if you don't want it anymore because you'll have written down the right answers on here from which to study. Also, of course, you need to double check. When I go over this, you may want to check yours and say, oh yeah, hey, Mr. Mars, I wrote A, but I erased it and then I put the right answer and then it marked it wrong because it saw I didn't erase it cleanly. But don't lie to me, okay? If you bring this up to me and you're like, yeah, see, it's right there, I'm gonna know, right? I'm not going to believe that every one of you did that, okay? So be honest. Carry on with your work.